Topic. Anybody have anything about project 5, homework 4 that they want to ask questions? Yeah.
So in the C file, the compiler.c, when it's reading the data structure once we've built it,
Yes.
for if statements, it does not do a PC next. So why is it designed that way? It's just
That is the way it's designed. So that's part of the project is you don't have any control over the back end. You know how it works and you know the data structure's there. So you have to create the input to get it to do what you want to do. Right? Because from its perspective, an if statement has a condition and then has a true branch and a false branch. Right? And so it does do the next instruction that it executes. If that condition is true, it will go to start executing at the true branch. If it's false, it starts executing at the false branch. Those are just the semantics of the back end if statement. Yeah.
For the homework, what happens on the stack when you call a printf?
What happens on the stack? Does that come into play?
Yeah, there's printf in the last question with it, which is throughout the stack response for it.
But what happens when a function returns?
Oh.
Is it going to be on the stack anymore? Exactly, right? So what's actually on the stack above the currently executing function? You don't know, but you know something about it. If there are other things that are on there. So that there's something that called it, right? So it's you can think about the execution trace, right? So the function above you on the call stack is the function that called you, and the function above that is the function that called that function, and so on and so forth all the way up the stack. All of those functions above you haven't finished yet. That's why they saved everything to the stack and called the next function. But then once you return, you're gone and you're not on the stack anymore.
So that's okay. Thank you.
Yeah. More questions? Please better than none. Anything? Homework. Project 5. Midterm next Wednesday. So focused on not having class on Wednesday, I forgot. Yeah.
Are we gonna have a study guide like we did?
We'll do practice. So I'll release probably on Wednesday. I'll do a practice midterm, and then on Monday next week we'll do practice midterm on Monday, and then on Wednesday we'll have the actual midterm. Yeah.
For this homework, for the first problem, did you want us to like the table?
What was the first problem? Well, I don't remember because I just create it and then you all do it. But what was it? Structural equivalence. Yeah. So what was the question?
So would it be easy to show this, I guess, just table?
Yeah. Exactly. Yeah. You should go through that truth table, assume that everything is structurally equivalent, and then go through trying to disprove structural equivalence when you can. And then just like when we did first and follow sets, if you go through and change something in the table, then you go through it again. And you keep doing it until you found out everything that's true that is structurally equivalent and what is not structurally equivalent.
Even if some of the variables have not the structure.
What do you mean some of the variables? It's types, right? So it's all types.
Yeah. And I guess it's like 7 types.
It's not that big with computers, right? Yeah.
You said last class that you were possibly going to keep your office hours on Wednesday. Is that still true?
Yeah, that's the other announcement. So I'm going to have to move my office hours today to 5 o'clock. So instead of right after class, I'm moving to 5. So 5 to 6. So in response to that, yeah, I'll keep my office hours on Wednesday. So if you want to show up, I'll be there. Anything else? Going once? Going twice? Sold. All right, so I made a slight change of plans. We're not going to go over lambda calculus today because I want to keep you focused, and because lambda calculus is pretty in depth. So I don't want to go over it now, and then in 2 weeks have to be like, hey, remember that thing we talked about with all these crazy lambda symbols? And you'll just kind of like. So we're going to save that until after the midterm. So talk about is we went over that. So what are the 3 types of memory allocation that we talked about when we talked about semantics? Memory allocation, not parameter passing. Yeah. Wait, well, let's go. So what are the 3 types of parameter passing? Pass by a name? Pass by what? By value, and then by reference. Okay, good. So those are different ways to pass parameters to a function. So what about the different types of memory allocation? Yeah. Stack. Heap. Global. Yeah, static. Yeah, exactly. So those are the 3: global, stack, and heap. So what have we actually seen so far about how it's implemented? Stack. Yes, please. Somebody say that, right? We went over in depth how the stack works. What about global? Did we talk about global allocation?
Yeah.
Kinda. I mean, we looked at it, right? We basically said the compiler puts it in global memory, and that place never changes, right? So we did look at that. Did we look at heap allocation? No, not really. What do we know about heap allocation?
It's persistent from function to function.
It's persistent from function to function. Yeah. What else do we know? Yeah.
It's whenever we call new or malloc or
Yeah, so we have to call, the programmer has to call malloc or new to get some new memory that persists between function calls. What else? Yeah.
The programmer has to free the memory as well.
Yeah, the programmer has to manually deallocate the memory, right, by calling free. So that's kind of the, with great power comes great responsibility, right? It's like, well, here's some memory that will persist after this function leaves, and you can tell me how much memory you want, but you as the programmer, you're saying, okay, I'll take care of this memory and I will free it responsibly. Yeah.
The stack and the heap share the same area for memory. They just start on different ends and grow in different directions.
I'm not sure that we talked about that. Did we talk about that?
Well, it is.
It's true.
It's true though, trust me, I know it. Yeah, so yeah, we're actually gonna look at that, but yeah, so they're all in the same address space, right? We really didn't kind of get into that. So we talked about, okay, the programmer must manually ask for memory allocation. The programmer has to actually explicitly release the memory back to the system, right? So unless it's Java, right? So why not in Java?
Because it's garbage collection too.
Garbage collection, yeah. So Java and other garbage language with garbage collection will, you as a programmer can alloc memory, you never have to free it because the compiler, or not the compiler, but the runtime environment will go through all the memory that's been allocated, see what's being used, not being used, and what things it can free. But that's more of an advanced topic because before we even need to think about that, we need to think about, well, how does C work when you malloc memory? Right? Where does that memory come from? How does it get to our program? Because the JVM, right, is using the C language. It's written in C or C++. I don't really know, but it doesn't matter. It's using that language, so that memory comes from the same place. So when you need to call malloc or free, what libraries do you have to include? Where are these functions defined? Are they part of the C language?
C library.
The C library? Which library? Yeah, standard lib. What are the memory allocation functions? And what do they mean? Malloc. What was it? Calloc. What's the difference?
It initializes the malloc does not initialize the memory and it initializes the value.
Yeah, so that's why we're using calloc in the program, in some of the code that we gave you, right? So it initialized the memory all to 0. Otherwise, if you just call malloc, you're just getting some chunk of memory. Good. Malloc, calloc, any other things? I'm gonna go somebody else. Yeah.
Like realloc.
Realloc. What's the semantics of realloc? Like, it doesn't have to be precise, high level semantics.
It's pretty similar to malloc, but except it's used for like when you've already allocated memory on something before, like allocate it to heap. Sort of.
Like deallocates then reallocates.
That I don't know actually. Yeah.
So when you allocated memory from the heap and you run out of space, you want to take all that information without having to rewrite it. So realloc will automatically reallocate that entire used memory back into the larger space on the heap, right?
Right. So I think that's the important little difference, right? Is it basically malloc? You say, hey, give me 10,000 or give me 100 bytes, and it goes, okay, bam, here's a pointer to 100 bytes. Do it with it whatever you want to do. calloc says, give me 100 bytes and make sure that they're all zeros. Okay, pretty easy to do that. Realloc says, hey, here's a pointer, increase its size now to 200 bytes. And so maybe it can just do that magically, or maybe it has to find more memory, copy over the previous 100 bytes into our 200 bytes, and then resize it and then return that to us. Anything else? Yeah? Free. Yeah, we need to be able to return the memory. What are the semantics of free? What was it?
You have to previously malloc it, otherwise it'll throw it.
Yeah, so can you just pass any pointer into free? Why not? What if you try to pass the address of a variable at a stack allocation into free? Why isn't that allowed? Yeah.
Well, doesn't it throw an error at compile time saying that you're free more than once, that you're free memory that
I don't think in all cases the compiler will be smart enough to detect that. Because you can think about very complicated execution paths with multiple function calls. How's it going to know that, right? In very simple cases, compilers can detect those things, but programs can get incredibly complicated. Yeah.
If heap memory is defined in the same address space as the stack, but the heap memory starts at a certain address, won't those functions only be valid for that address and forward?
Yeah, that's a good way to think about it. Yeah, as we've said a lot, right? It's because that's what the semantics are. The semantics of free says, give me a pointer to something that was returned from malloc. Otherwise, I can't do anything with it. And I'm pretty sure if you try it, there'll be an exception or some segmentation fault, which would actually be something really fun to try. But we'll actually look at kind of why that is that it does throw an error. So these are defined so they're part of the C standard library, right? They're not actually part of C, the language, right? Kind of like Java has a language and then Java has a standard library, right? Those are two different things. So what implementation of malloc, calloc, realloc, and free are you using in CentOS? What was that?
The ones that are in glibc.
Yeah, the ones that are installed in your system, right? That's the whole thing. So your program, you write your program, it uses some standard libraries, and those libraries are present on your system. Are these the only ones you could ever use? No. Yeah, there's multiple implementations. In fact, hopefully you'll be so inspired after this lecture that you'll spend all of Wednesday, or maybe Tuesday, because Wednesday's a holiday, so you should be honoring veterans. But on Tuesday, you'll write your own implementations of malloc, calloc, realloc, and free. And you can do this, right? Because you can provide these library functions. There's nothing that says that you can't. And in fact, there's actually a lot of computing scenarios where you actually really may want to do this. So can anybody think of why? Yeah.
Performance.
Performance, in what aspects?
Sometimes for certain program types, you want your allocation pattern may be different than the one that's assumed by the standard functions. So it might be better to use a different one that fits your allocation pattern.
Exactly. So yeah, your program has a certain way of allocating memory, right? They're all kind of different. Is it lots of little things? Is it lots of big things? Is it one big thing? All kinds of ways, right? So you could, when you're doing profiling, you could say, actually, it's a lot of time being spent in here. Maybe I should think about a better way to do that. Any other scenarios? Maybe like an embedded system, right? Like a Raspberry Pi or something. It could be that there's not really a lot of memory, or maybe that has specific constraints. Maybe you actually don't ever want to call these functions, so you want to throw an error when somebody tries to call them, right? So that way they crash. Yeah, what would be another reason? Yeah.
Potentially security.
Security, yeah. You could maybe want to do some kind of secure wrapper around these things. I was even thinking about that. Because you want to learn, because you desperately need to know how these things work, so you want to write your own to understand how it works. Right? All totally legit reasons. Questions? Maybe you have a better idea for a new malloc system that's going to be faster in all kinds of applications, and so you'll write your own. Could happen. All right, so now we're going to look at a program. So now we want to say, okay, how do these functions actually work? So to get some idea of that, we're going to run through just some executions of seeing what happens when we call these functions, seeing what they return, seeing what we can learn about them from interacting with them before we kind of dive in and see how malloc kind of conceptually works. And then we won't actually go into how it actually works because this thing's been around for 20 plus years and is very optimized and is very crazy, but we can talk about the general concepts. Okay, first thing we got to do, we got to include the standard lib.h, right? Because that's where malloc and free and those functions are defined. We're going to include standard out. We're going to define our main function. We're going to have a local void pointer called test. We're going to have a local integer I. What kind of allocation are these variables?
Static.
Static is global. That's why we use different terms. Global, stack allocation. Then we're going to find the size as ATOI of argv1. What is this doing? What's in argv? What was it? Yeah, arguments that are passed to the function from where? From the command line, right? Exactly. So you did this in project 3. So you implemented the, I mean, we gave you the code for it, but you did the code to parse in that parameter. So why am I doing argv0 and not argv1?
argv0 is the name of your program.
argv0 is actually the name of the program, yeah. So you execute the program, and what gets passed to the program is the program name in argv0, and argv1 has the first command line parameter if there is one, argv2 has the second if there is one. What's in argc? What was it? Yeah, size of argv, so that way you know, right? So the program otherwise has no way of knowing how many arguments are passed in. So I'm being super lazy, I'm not checking argc and doing all kinds of fancy error checking. So what's ATOI doing? Yeah. Right, converting it from a string into an integer in what base? Yeah, by default base 10, I believe. I think there's other ways you can specify different bases. So, in effect, what is this allowing me to do? Yeah.
You put in, when you call the program, you put in the first parameter on the command line as the size of whatever it is.
It doesn't matter where this is being used, but we know that whatever I pass in as the first argument on the command line, that's going to be interpreted as an integer by the program and going to be set to this size local variable. That's all it means. Okay, then we got a for loop. We're going to loop from 0 to 10. And we're going to say, we're going to malloc new memory. How many bytes are we going to malloc?
10 times size.
10 times size. Why 10 times size? Yes. Okay. We're calling malloc 10 times, but just in this call,
Oh, yeah.
how many?
Once. Oh, the size, just the size.
Size, yes. You got it. You're saying all the right things. Yeah. So we're mallocing size, which is whatever we passed in. So what's malloc return? Remember semantics? What is the semantics of malloc? What does it return?
Pointer.
A pointer to what?
A memory address.
Yeah, memory address, right? So circle box diagrams, it's returning a new address for a new box that it created for us. All right, and then we're just printing out test. So is this printing out what test points to? It's printing out the address of the pointer. So it's printing out the value of test as a pointer. Right, so remember function, so this is why we're bringing everything home, right? So C, pass by value semantics, so what gets passed into printf is the value of that address that we just got back from malloc, and then we're printing that out as a pointer, which means print it out in text, so it's easier for us to read. So this is the address of that memory that just got returned from malloc, yeah?
You would have made test in star, but size would have stayed the same size it is up there, and so you're trying to allocate to an in star arbitrary size. How does that work? Would that throw an error, or would it just be throwing? So I think what int stars are assigned to what the size of int, which is 8 bytes, I think, or 4 bytes.
You gotta say
Size
that
was
again.
like
So you're
what if
saying
size-
so
what if
let's
size
take a
was-
step. Let's take it step by step. So what happens if I change this void star to an int star and change nothing else? Would it still compile?
Yes.
Yes. Because you're allocated. What if
Would it
you're
throw me
allocating
any
15
warnings?
bytes to
What's the type of malloc? What's the signature? Yeah, it returns a void void star, and I'm trying to cast that void star as an int star.
But that works with C.
I think if you turn on all the warnings, it should give you a
No,
warning.
it
No?
doesn't give you warning.
Explicitly,
C++.
implicitly convertible to any type.
I thought it was the other way, but okay.
No.
All right, so you could do that, right? So you could do that. Does that change how many bytes are allocated?
No.
Why not?
Not just.
Yeah, because it's just test, right? So, or size. Whatever we pass in as the size, that's how many bytes are allocated. Not, it doesn't matter what the pointer is, right? That affects how we use it and how we interpret that pointer. Is there more? That was it?
I'm kind of.
Did that actually answer your question?
Well, I got kind of wrong with it. So it does throw it throws a warning and it
I don't know.
works.
Maybe not. Probably not.
C++ it throws a warning, C it doesn't.
Cool. All right, and then we just return 0. So if I compile this, is there going to be any errors, warnings, anything wrong with this program?
Memory leak,
Memory leak, in what way?
because after each time you iterate through, you lose the address of the malloc, so you can never get it again. So it's memory that's allocated and never be able to use.
Which is, what is another term for that?
Memory.
Somebody said it. Garbage? Garbage, yeah. So if you were asked on a test, what would be garbage memory at these places, that would be the answer, right? Because all those 9, well, 10 because they're never free, but yeah, all of those 9 memory allocations are being allocated and going nowhere. But is that going to give any errors or warnings?
Nope.
No. Right? It's not. Is anybody complain that we didn't free that memory?
You didn't have enough memory to blow up.
We didn't have enough memory to blow up? We'll see, actually. Okay, so it compiles fine. So if I run it and set size 4, so how many bytes do I want to malloc? 4 bytes, right? So those are the pointers that I'm returning. So the first one just returns me whatever, 408A008. So now what's the next one? The address of the next thing that's going to return. Is it going to be 804A00C? Why would it be that? Why did I just say C? Because plus 4 bytes, right? Because that would be 4 bytes above this. Or could it be 804A004 if it's going down, right? I don't know. Do we know anything about the heap at this point? Not really, except that it gives us addresses, right? So okay, let's look at it. So then the next go around, it returns us 804A018. So what's the difference between these two? 16 bytes. In which direction? Yeah, we didn't specify direction, but up, right? If we're thinking about the way the way we laid out the stack, right? So is this what you expected? Sort of? What was what you expected and what was not?
Well, it's still like the 4 bytes difference between addresses.
The 16-byte difference.
Yeah, that's what we do.
Yeah.
That's what I-
So what's the next one going to be? 30. 408 or 804A0 what? 38? 28? 23? 112? 28. And it keeps going like that. All 16 bytes after each other. Until we've gone 1, 2, 3, 9 times. Or 10 times. Yeah, I'll make sure that my world made sense.
So why does it go up 16?
Why does it go up 16?
4 times.
Let's look at 8. What happens if we do 8? So what's going to be the first value that returns? Is it going to be the same thing?
Doesn't have to be.
Doesn't have to be. Why?
Could be other stuff on, I don't know, it could be different.
Yeah, it could be different, right? There's nothing that says it has to be. And in fact, on a modern machine, it's always going to be different for security reasons. A side note, there's a technology called ASLR, which basically continually shifts the address spaces. Because if an attacker can't predict where your stuff is in memory, it makes their job more difficult. But I had to actually disable that on the system to show this, but when you do disable that, you get the exact same things every time. So this is what it did, 804A008. So what's the next one going to be? So how many bytes am I allocating this time, or mallocing? 8. So it's going to be, what? 18?
I think it's 32.
Do you want to take, maybe I can't condone gambling, but do you want to take imaginary dollar bets on this?
3-8. Penny on 18.
It's too much. Too much. It's still illegal in Arizona. Okay, so turns out it's the same. What? I know. And then above that, and then it keeps going. Bam. What if we increase it even more? Let's say we want to malloc 24 bytes. The first one, different, same, same. Turns out to be the same. What about the next one?
2-8.
2 8? 112? 18? 2 8. So why can't it be 18?
I don't know.
Yeah, there's not enough space in between, right? So if we said that if you gave me 24 bytes and said, hey, start here, this is your buffer, here's 24 bytes, it starts at blah, 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 08. And then I asked for another 24 bytes that started at 18, only 16 past that. Now I've overlapped buffers, right? And so that would be a memory. That would be a very, very bad and really difficult memory error to figure out. So this is good that it's doing this, right? We want it. This is the behavior we want. Yeah, so that keeps going by I want to say 2s, but it's really by 32s. Okay, let's crank it up a little bit more. What about 4096? So is this a reasonable thing for me to request as a program? Yeah, that's not even that much memory, right? That's like what, 4K maybe? Or yeah, right? That's barely anything. So what's the first one going to be? Same? Different? Same? What's the next one going to be? Stretching hex map. Yeah, it's hard. Yeah, so it's actually, it will be at 804B010, 18, 4D020, and it keeps going on, kind of in this way where it's iterating over the 1, 2, 3, 4, the fourth digit, but also by 2. What if we do something really big? Is it going to cause our program to crash? Possibly. It's going to grind my computer to a halt. It's using all of the machine's memory. I don't know. So what do you think the first thing is? Is it going to be the same? A little different, right? What's the difference between those two? I'll just say I don't know. It's big. It's very big. Right? So what's the next one going to be? Is anybody noticing a pattern? So what's the other thing that's really interesting about this one? That's decreasing, right? Right. What were the other ones? Increasing. Yeah.
So it's just cycling through the entire thing.
So what's the next one going to be? Is it going to wrap around? Is it going to crash?
So is that, because it's so big, it's exceeding the size of
So this number's still less, because remember 2 to the 32 is what? 4.7 billion or something like that? It's actually larger than this number. So this is what I did is I started from that number and then divided by 2 every time until I found a number that worked well for what I wanted to demonstrate. Yeah.
Well, so aren't you allocating of about 5 gigabytes?
5 gigabytes? I don't think this is, I think it's like 5.
Well, because that I think is 500 megabytes.
Yeah, 500 megabytes, exactly. Yeah.
So that's each time. So
Yes.
you get a total of 10 times.
Yes,
So that's a total of 5 gigabytes.
correct. So what's going to happen next?
So at some, and since you're using it in 32-bit, then depending on if the physical address extension, then it may or may not crash.
Isn't it doing some weird paging stuff?
It definitely is doing some weird stuff. Well, what's going to happen next? So we've basically allocated, in 500 meg chunks all this memory, right? And so with 2 to the 32 is what, 4 gigs basically? Something like that, is that right?
Yeah.
So if we're trying to allocate 5 gigs, we only have 4 gigs that we could ever possibly allocate, not including the area for the stack and the area for the code and all that stuff. So from this pattern, are we running out of memory? Right, because the next one should be decreasing by, it's not 2, but whatever 2 is times 32 at that offset. So what are the semantics of malloc? Let's go back to the semantics. Anybody crazy enough to be running some version of Linux on their laptop? You want to do man malloc and read us the man page of malloc?
I'm actually on right now. So,
That's cheating. No, just kidding. What does it say? What does it say malloc returns? In your best. Just kidding.
Well, yeah. Returns allocate size bytes and returns a pointer to the allocated memory.
What we've been doing. Good. Perfect.
Yeah, but also too, this is important right here that with Linux systems, it follows the optimistic memory allocation strategy. So this means that even when malloc returns a non-null, there is no guarantee that the memory will be available.
That's scary. Keep reading. What else? What else about the return type?
About malloc or?
Yeah, about malloc. Specifically malloc.
Okay, if the size is 0, then malloc returns either null or a unique pointer value that can later be successfully passed to free.
Okay, also weird. Continue.
That was for the malloc line. So the malloc and calloc functions return a pointer to the allocated memory that is suitably aligned for any kind of variable.
Okay, so that means it's gonna align. It's not gonna give us like an odd memory. It's always gonna be, I think, 8 byte aligned.
Yeah.
Which is actually what part of what we can see here.
And then it says on error, these functions return null.
So on error, these functions return null. So what would trying to ask for more memory than the system can give you? Yeah, it should return null. So is that going to crash our program?
Nope.
Why not? I'm getting a null pointer. Shouldn't this be a null pointer exception?
You're not trying to access it.
What was that? Yeah, I'm not. Am I ever dereferencing test? Oh, so it's not gonna. So it shouldn't throw an exception, right? It should just output null, which it does. Which is weird. I didn't know this program did this, but I didn't know printf did this. So this is all on CentOS 6.7, everything you guys have been using, compiled for 32 bits. So it just returns null, and then what happens when we call it again? Null, null, boom. Done, right? So our program actually didn't crash because malloc actually has a way to tell our program, hey, something went wrong and you didn't actually get the memory that you thought you were going to get. So should you be checking for that in your code that you write?
Every single time, check to see if no. Safety. Safe.
Yeah.
There are divided thoughts on it.
What was that?
There are divided thoughts on whether you should check.
What's your thoughts?
Well, typically if you can't get the memory, then you're not going to be able to do what your program wants to be doing anyways, and it would be almost better to just let it crash and die.
Yeah. So yeah, it's a tricky thing, right? 'Cause it's like, well, if my program needs this memory to run, which is why I'm asking for it, if the system can't give it to me, then how can I just continue executing if I don't have that memory that I need? On the flip side, if you don't actually check for it and die there, maybe it dies later in another function, so it's hard to tell where that memory couldn't be allocated and why you got a null pointer to this specific variable. Yeah?
So then, the thing is, it can also be tricky to tell it to exit there.
Yes.
Because sometimes those functions themselves can call malloc.
So yeah, if you want to die and quit, right? You could call assert or abort. I don't know. There's all kinds of functions. Exit. Those functions themselves may want to call malloc and call printf to print out some debugging things, but your system's out of memory, so maybe you'll crash while you do that, and then you have this weird thing of like, why is system.exit crashing? That doesn't make any sense. So yeah, it's actually a really big problem. One way you can think about maybe like a database or something wants to use as much memory as possible, so it like tries to malloc a large chunk of memory and then keeps, when it can't get it, it keeps going smaller until it can finally, you can think about maybe if it's not something that you desperately need, but you're trying to reserve that memory, maybe in that case it's nice to know that you couldn't get it. But yeah, it's one of these really weird kind of edge cases where it's like, it's kind of like in Java when you have to catch, don't you have to catch that exception when you write out like system.out, or when you read in or something like that? Is that what it is? When you read in, you have to explicitly either throw an exception or catch that exception. No, do I not know what I'm talking about? Right? So it's like, well, what are you going to do if you can't read from the keyboard? Like, what could you possibly do? Your program's never going to execute. Anyways, it's one of these cases. Okay, so what do we learn about the heap from this little exercise?
You can grow both ways.
The heap can grow both ways.
Up and down, that's weird.
Up and down. Yes, that actually is really weird. I have theories, but we have to go through it. What else did we learn? But mainly, what did we see it grow? Up. Yeah, so we saw it growing in up addresses, right? It would keep returning us addresses higher up in memory. What else did we learn? Yeah.
Has a minimum size that it will allocate?
Yeah, it's a minimum size. It's allocating at least 16 bytes, even if we only ask for 4 bytes. And it allocates the same thing even if we ask for 8 bytes.
It can grow to a pretty large size.
Yeah, you can actually get a decent amount of memory out of the system, right? Which is kind of nice if you needed it. Anything else? Or anything? Yeah.
Does it always increment in the same way? Like it went from 8 to, or 16 to 32 and to 64? It seems like it would increment.
Yeah, seems interesting. All interesting questions. Okay, so it helps to, we're going to look at the kind of memory layout we're even looking at. So from all of our diagrams of memory, what's the top? What address? The highest one, all F's, right? I'll say it since I made you all say it. F, 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 F. Wait, I lost count. F, 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 F. 8 F's. What about the bottom? Oh, shoot.
0, 0, 0, 0, 0.
Yeah, or just 0, right? Same thing. Okay, so what's at towards the top of the stack that we've been talking about? What was it? What did you say?
The base pointer.
Base pointers, yeah, it's part of it. Caller functions also. A big region of memory that.
Actual code.
Stack. The stack, right? The stack is, and which way does the stack grow? Down. So the heap actually is then below the stack in the lower portion of memory. And so the stack's growing down. Which direction is the heap growing? Up. Yeah, it's kind of cool, right? So you kind of start the stack up here and the heap down here, and then they can kind of like grow as need be, and if they ever cross, you're going to have massive problems and everything's going to go to heck. Questions?
Aren't you supposed to store the code of the program somewhere between?
Yeah, the code of the program is usually, I believe, actually below the heap. It's usually somewhere here, at least in the normal allocation, but there's nothing special that says it has to go in this specific location. But yeah, you definitely don't want to put it in the middle, right? That would be bad if somebody could overwrite it.
I think your mic went out.
Huh?
Your mic went out.
Oh, mic went out? Hello? Is this what that red battery light is? All right. Always fun changing a 9-volt battery in the middle of class. Right. Questions while I do this? I don't even know which way to push. Or just like smashing it. Okay.
Do you feel pressured having all?
Yeah, I do actually. It's really, you guys are, oh, there we go. Got it. Got it. Solved it. Right. This is why I'm not in the, that's a dead battery. 50-50 chance. Oh no, which one was which? I think it's this one. Okay, how about now? Hello?
Good.
Hello? Okay. We have 1/2 of a bar. Otherwise I'll just start shouting and it'll be really awesome. Okay, great. Okay, so how does this actually happen? So is malloc moving this stack up? Yeah, there's a question?
Yeah, I was gonna ask, what if...
You couldn't ask while I was like doing the batteries and...
I was
Yeah, it gave you time to think. I'm just teasing.
Okay, so what if your last program you take up all the space on the heap, and then after that you run some infinite like recursive program that takes up places on the stack? What would happen there?
You're gonna crash at some point.
So it would crash.
Yeah. Yeah.
So there's no space on that.
Exactly. There's no space anywhere, so yeah, you're gonna run out of room at some point, and something's gonna crash. Yeah, where exactly it crashes? That's a good question. All right. Okay, so is malloc doing this? Is malloc moving the stack for us? Yeah. No? Is that what the man page tells you?
Yeah, it says that a program called sbrk.
Okay. It's not a program, but yes. Okay.
Or functions.
Okay, so yes, so it turns out malloc itself doesn't actually control the stack, which is kind of crazy when you think about it. But so what actually happens is there's a system call. So the Linux OS has a function called sbrk, which will increase the size of the heap, or alternatively, if you give it a negative number, will decrease the heap. And it's defined in this header file. And this is the signature. So you call sbrk, you give it an increment how much you want the stack to move, and it'll return a new pointer to that, I believe, the old location. So you'll get it will actually move the heap and allocate memory for you, and it'll give you a pointer to that last location. So this is actually nice in some ways in that malloc is not doing anything special, right? Malloc is not allocating new heap. It's actually just asking the operating system to allocate more heap. So let's look at how that works. So here I have pretty much the same program. I'm going to loop, same thing, right? I just added one more local variable called current break. I'm going to call malloc, so I'm going to malloc some memory. And then I'm going to call sbreak 0. So what does sbreak 0 do? This is awesome. We have our human man page.
It finds the current location of the program break.
Right. So this will return a pointer to the current location of the heap. So I'm passing 0, so I'm not changing it, but I could if I wanted to, right? It's just a system call. I can make that as the program, or malloc can make it on my behalf. And then I'm going to output what we got back from malloc and the current break, the current location of the heap. Then we're going to return 0. Yeah?
This is kind of off topic, but when you say it's a Linux system call,
yes,
but it works, obviously you can use these dynamic allocation functions on other systems. So sbrk works on all systems then?
Not necessarily. So the malloc implementation has to use, this is one of the nice things, is that abstraction means that you can write a general malloc that can operate if it has a function to ask for more memory from the stack. So on Linux, it's sbrk. On Windows, they have some other way to do it. I don't know exactly what it is. And on Mac OS X, they also have, I think, probably different and similar. Mac OS X is weird, so I won't get into it. But yeah, so yeah, this is all just defined, so you can do this. Okay, so is this going to give me any errors? Warnings? I hope not, right? So it's pretty much exactly the same except for the addition of one local variable, one function call, and slightly changing the print statement, right? Okay, so let's run this with 4. So what's the address that malloc returns? Is it going to be the same as when we previously called 4? Doesn't have to be, what do you mean?
Well, another program could be running the allocated memory in the Heap, so it would be different now.
True, doesn't have to be, except every process sees its own memory. So you don't have to worry about any other processes. That's what the operating system handles for us. Good question. Yeah? What's sbrk? What's sbrk going to return? Is it going to return the same thing that we just malloc? Like, are they going to be the same? So malloc, when we call it, it says, okay, they need 16 bytes, and then let's first move sbrk up, change that, and then return that memory to them. Same? So this is the same, right? So what malloc returns is the same, which makes sense, right? Where it's pretty much the exact same function. And we've removed ASLR, so that doesn't change at all. But sbrk returns something much higher up, right? So what happens, so now when I call on the next iteration, what's malloc going to return? 18. What do you think about sbrk? What's it going to be? Same? Why the same? What does this effectively mean?
How much memory that you have to be able to allocate what they need.
What was it? Let's look. So what would that mean?
It's asking sbrk to give it more memory than you asked for, so it can just not call sbrk again.
Right. So when I called malloc, right, it seems like it moved. It reserved a bunch of memory from the system, and then gave me 16 of those bytes at the bottom. And the next time, it gives me the 16 bytes after that, and then the 16 bytes after that, and so on and so forth, all the way through. And it never actually has to move and ask for more memory from the system, because it's already got, we haven't crossed this threshold, right? We've only allocated maybe this much of that memory, something like that. So why would it do that? Why would it pre-allocate? Yeah.
Probably so that that memory chunk is reserved for this program. It's easier to read sequentially and saying, hey, it's all here. It also takes more time to, if it only allocates that memory once, you don't have to spend time allocating it again.
Right, so if we think about it, even if it's relatively cheap, I still have to go from my process to the operating system to ask for something. It does whatever things it does and then returns me back more memory, right? That's a lot more than when I'm called malloc. That's a function call in my local address space. So that's a very quick function call. So it's a lot slower to go to the operating system than it is to come back for various reasons. You'll find out in your operating systems class.
Wait, so the first time it does an operating system call, and the rest of the time it doesn't?
Unless it pre-allocates it, even when it initializes, they could have some malloc initialization thing. I'm not exactly sure if that happens or not.
What about the fact that your C program will, even though we don't explicitly free memory on accident, it'll still free it. Does it have to do with that? Like, in a way, when we stop running our environment or something like that, anything that we forgot to free will be free.
Correct, because the OS knows this is that function, this is that program's memory. Bam, throw it away. It's all gone. It can be reused. It doesn't matter.
That sequential, is that sequential space have to do with that?
I don't think so. I think it's mostly just performance. It's saying like, okay, well if they called me once, they're going to call me multiple times, right? So I might as well store some memory. And however much this is, that's not that much. It's what, I don't know, 10 megs or something? On a modern system, that's like nothing. I don't know, very much just guessing, but reserve some memory, and if they use it, if they stay within that, then I never have to bother the operating system again. Okay, let's do bigger. What if we do bigger, 1024? Okay, so same, and now we're going boom, 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 boom. So we still here stayed underneath that break. All right, let's make it a little bit bigger. Oh no, I didn't. Okay, so 4096. This one's actually very interesting. So is the sbrk different? Yeah, but it actually did it the first time. It actually allocated more memory based on our first request. So these things are very smart, or maybe not, depending on how you look at it. All right, let's bump it up even more. All right, so here I'm asking for, I don't remember what power of 2 this is. 10, something like that? 16? 16? Okay, cool. So it returns the same pointer again for malloc. Now sbrk is 807B00, and then it increments, goes to 805, 806, and now it's going to have to call sbrk, right? Because I want more memory than the operating system has allocated to it. And so when we do that, we can see that actually it goes and gets more memory, and then gives some of that memory to me, keeps that, while it services more requests. And then when it runs out and it says, oh, we need more, it goes to get more from the operating system. Questions on this? Oops. Yes, so that's part of the semantics of sbrk. So it basically starts here and it says, okay, give me 100, whatever. Your system can say, increase this heap by 100. So it can increase it, and that says, okay, all of this is now yours, right? And you say, increase it 100 again, and it increases all that. So yeah, it's all contiguous memory. Because you can only increase it or decrease it. Those are the only two directions. So if it's not available, it'll error, basically. Like sbrk will throw it. Sbrk will signal to malloc that it couldn't give it the memory, and then malloc will return null.
So we include this available memory somewhere else.
Exactly. Yeah. Okay. So we can see from this, we learned that malloc is calling sbrk to request more memory. So that's pretty clear, right? But then what is malloc returning to us as programmers? Yeah, it's a portion of some of the memory that it requested. So how is that actually being freed? So think about it. So now we know that malloc is not doing anything special, right? All it's calling is this system call to ask for more memory, and it can increase it up or down. But now when we pass this thing back to free, I want you to think about, well, how does that actually get free and deallocated? Like, what do I have to do that? So to do that, let's look at an example. Okay, so exact same thing, but I'm going to free test. Right, so I malloc something, now I fixed I went, oh no, there's a memory leak in my program, I'm creating garbage, so I'm going to free that. So, see, exact same thing. So now I run it with 4 bytes, what's the first thing it's going to return? At 08, the same thing? Is the free going to change anything?
Not the first time.
Yeah, not the first time. It better not, right? Because nothing changed up till that first call to printf, right? They're exactly the same. And we can see that, yeah, this is the exact same memory address. So next time through, what is it going to malloc? What address is it going to return? It's the same one, a different one, something 16 above it. What was it?
Depends on the malloc.
Yeah, it depends on the malloc, right? It's giving us no qualms about what it's doing, but of course, we're kind of peeking under the hood a little bit, right, by even printing out these pointers. So yeah, we can see it actually reuses it, and it just keeps reusing that memory and saying, okay, well this, because when we pass that pointer back to free, what did we tell malloc? What was it?
We're no longer using it.
Yeah, we're no longer using it, right? We're no longer using that pointer that you gave us, so you can reuse it, yeah.
But is it freeing the entire chunk that sbrk returned?
What does this say?
Well, all that's saying is, well, is that not really telling us whether that whole It's, I guess not, because it's going to the same, it's starting at the
Right,
same
'cause it's
exact
staying
place.
right there, right? So it's not ever decreasing. And this makes sense because it's the first allocation. To your larger point, I actually don't know.
I mean, shouldn't, if you weren't using any of that larger chunk that sbrk gave you, shouldn't the system by default just free that back?
It could, yeah, it could. Okay, so this is interesting, it does that. So let's do more memory, so we always want more. So now what's the next one? Is it gonna be the same, different? Same? Yeah, right, it's really lazy, so you tell, but notice here, so what's the difference between this and the previous example? I think it's actually the same. Yeah, same. Ooh, this is nice. I like that. So what's the difference here? There is none. There better be some difference. Is it? Am I running these programs exactly the same?
Well, you allocate more memory, but the same memory is still being freed, so.
The same memory is still being freed, but how much memory is being freed? 1,024 in this case, and how much in this case? So how does it know? Let's look at another example. Okay, we're going to slightly change this, and we're going to say every odd iteration, we're going to free test. So we're only going to free half the time. Okay, we're going to compile it. It's going to compile fine. We're going to malloc 4 bytes. So now, okay, we're going to have the same thing. What's the next one going to be? Are we going to free? What's I on the first iteration? Is 0 odd? 0 even? Yes, so we're going to free. So then what happens the next go around when we malloc memory? Same. Okay, oh wait. Now, when we call malloc, now what memory is it going to give us? 18? Because we didn't free that? Now we're going to free this memory, right? Because this is the 0, 1, 2. 2 is even, so we're going to free that. So then when we come back around, when we call malloc, what memory is it going to give us? Is it going to give us 08? Why not? It's still being used. Exactly. So it's going to reuse that 18, and then the next one's going to give us 28, and so on and so forth. Oh no, I don't have the example. Okay, so, but how did it know? So how did it know to only free 4 bytes here, and not to free 1024 bytes? What was that? Yeah, because we told it to, right? When we called malloc, we said malloc 4 bytes. And so it has to have some way of knowing to associate 4 bytes to that pointer. So what's actually happening, and we'll get into a little bit, is it's doing some internal bookkeeping, and that's why it doesn't just allocate exactly how many bytes you asked it to. It allocates some bookkeeping bytes too, so it can keep that size in there, in that memory that it gives you, in a place that it can find it later. Okay, so we need to do this. So we need to call malloc and free. So these are the semantics. So how would you do that? So what would you use with malloc to increase the heap size? sbrk. Yeah, we looked at it, right? You use sbrk, and you just return the pointer that sbrk returns, right? So you're saying, hey, here's some memory, boom. Okay, we do that. What about to free? So let's say you want to free something. But what would be something simple that would be the opposite of what you just malloc? Yeah, sbrk minus to some negatively alloc size, right? But the problem is you need to know that size. So you need to, using this pointer that you return from malloc, you need to somehow be able to get that size that you created. Okay, so the way it's actually implemented, and this is kind of generally for all malloc implementations, you always want to reserve more memory than was requested, because you want to have some overhead, some bookkeeping bytes. And you store that size that was requested in the malloc at some fixed offset from the pointer. So that way, when somebody calls free and gives you that pointer, you know you can look at a specific offset to find the size of that pointer. Is that kind of making sense?
Where's the fixed offset?
Exactly. I mean, it depends on the malloc implementation.
I mean, could you put it right at that beginning of that address?
Could you put it right at the beginning? Let's ask. So, how is this pointer used?
How is the pointer used? How
Yeah.
do the programmer sees fit?
Yeah, as a programmer sees fit, right? So if you return an int star into some variable x, you malloc 4 bytes, put it into x. You can say star x is equal to something, right? And we'll store that value in there. So can you store the size at that pointer that you return? No, because specifically the programmer can mess with that, right? That's where you're returning a pointer to that start of that new memory that they can use. You're saying use this, go ahead, do whatever you want.
But you could put something in front of that.
But you could put something in front of it or behind it. It kind of depends on how you think about it. But yeah. So what if we did something like this? So let's create a struct. So this is, I've kind of adapted this slightly from the real malloc implementation that's on CentOS 6.7. This is actually the very nice thing about using like Linux and all that fun open source stuff, because when you have questions like this, like how does malloc work? You can actually dig into the source code, and this is actually very well documented. You can actually just read it, and it's pretty legible. So we're going to create a structure, right? This chunk, and that's going to be internal to us, to our malloc. And we're going to have a field called size, right? Because this is what we care about. This is that size that we need to keep track of. And then we're going to keep, after that is just going to be a void star we're going to call buff. I'm trying to think, I may have made a mistake, but that's fine. Okay. So when we define malloc, right, we have to follow this signature. If we don't follow the signature, then we're not actually implementing malloc.
Wait, doesn't this answer my question earlier about assigning an arbitrary size to int star? Since you're right there, you're kind of just making the size of the int star arbitrary without actually knowing what type of variable it's being assigned to.
Exactly. So yeah, this is why when you request memory in malloc, if you want to malloc like an array of integers, let's say you want to allocate 10 integers, you do 10 times size of int, right? And it'll give you a pointer to 40 bytes that you're free to use. And you can walk over all those 40 bytes and access all of those integers. But the programmer doesn't have access to this size that you gave it, right? This is our internal structure. What we're going to do is we're going to return to them basically a pointer to buffer, and that's what the programmer can use. But we're going to keep the size right above that pointer, and they're never going to know because they shouldn't access that memory. Okay, so we do some stuff in malloc. We're initializing things, whatever. It's actually very complicated, especially the way they do it. But there's actually really good, simple malloc implementations that you can go read. There's, I don't know, all kinds of stuff. This is not crazy, out of the world. I don't know. It is not rocket surgery or science. Yeah. So, all right. So this is basically what we're gonna do. So this is kind of in our very simple, stupid malloc implementation. We're gonna say, okay, we need more memory. So we're gonna call sbrk to increase memory, right, from the operating system. And we want size, right? Why size? What was that?
That's how much they want.
Yeah, that's how much the programmer wants, right? So we have to at least get that many bytes, otherwise it's bad. But then we're also going to ask for a little bit more. We're going to ask for a size of this malloc chunk, which I think actually will ask for 8 bytes, which is not exactly what I want, but that's fine. But we have a little bit of overhead here, right? So we're getting more bytes than we asked for. And now we need to store the size that they gave us, right, for this pointer. So we're going to store in this new memory the size that we gave as the chunk size, right? Makes sense. We want to be able to access this later. But now the question is, what do we return to the programmer? Buff, yeah, exactly. So we want to return. So what is new memory pointing to? Let's think about it. What is a struct in C? A location? A struct, I'd say, is like contiguous data, right? So we know it's size, a size t, which is just basically an unsigned integer, or actually maybe a signed integer. Doesn't really matter for these purposes. It's 4 bytes, a size, and then 4 bytes of whatever, a void star called buff. We actually don't care about that at all. But newmem, what does newmem point to? The start of the structure, right? So if I dereference the start of the structure, but I'm storing the size in there, right? So I definitely don't want to return that, because then the programmer could overwrite that. So what I actually want to do is return them that memory address that's 4 bytes after this pointer that I just got, which will point to where buff is. And so this is actually, I did lift this directly from the docs, or the actual code, adapted a little bit. Okay, so what is this doing? Let's unpack this. Okay, so it's taking newmem and it's casting it to a character pointer. Is that valid?
Yeah, you can always cast whatever you want.
Yeah, you can cast, right? It's an explicit cast. The programmer can do that. So then it's adding size of size t. So what's the size of size t? How many bytes? 4. So why did it do this char star addition here?
No idea.
Yeah.
Because you want the addition to occur in increments of 1.
Yes, exactly. So we know that so if you have an int star, an int pointer, and you increment it by 1, how many bytes does that move the pointer? Size of int, yeah, exactly, normally 4 bytes. And that's why you can use basically a pointer as an array, is you can iterate over that pointer, incrementing it by 1, and it's going to increment however many the size of that pointer is bytes. So if I did newmem plus 1, where's that going to point to? What was that?
8 bytes.
Yeah, 8 bytes afterwards. Right? That's going to point to 8 bytes into the sbrk, which is not really what I want. I want to return this address here. So by taking newmem, casting it to a character pointer, now I know I'm incrementing by bytes. I'm talking about bytes. So I'm going to move that pointer forward size t, which is 4 bytes. And I'm returning that. Right? So now the programmer can use that. Their pointer is going to point to right here, and they can use all of those size bytes, and we've allocated more than enough memory for them, so they'll be fine as long as they stay within those bytes. Yeah?
Is there a specific reason why these types of malloc protocols and other memory allocation protocols use size t instead of int?
Yes, but I don't know it off the top of my head. If anybody else knows, to be more clear, I would say, yeah.
Size t is just the largest size integer.
Okay.
Unsigned integer on the platform.
I think it's sign.
I think it's unsigned.
Yeah, I don't know.
I'm pretty sure it's unsigned.
Yeah, so so you can have different implementations do things. So you can have C, the same code, and you can change the pound defines of the different integers, because you can have, I don't know, ints be different sizes. You have 64-bit integers, but size be different. I don't know, whatever.
What we want to know is why is the void star buff necessary in the malloc constructor?
This? Oh, this?
Yeah.
It's not
Because
necessary.
you're not using it.
Correct. But it actually gives you a way to talk about that memory that's located there. They actually don't do it exactly like this, but you can. So you got to think about it. So, okay, what are we returning here, basically?
Buff star.
Yeah, we're returning a pointer to this buff star, to the buff, which is a void star. So now, when they call 3 with this pointer, what do we get back? Are we getting a malloc chunk? A pointer to a malloc chunk? No, what are we getting a pointer to? Buff. Yeah, exactly. So how do we get back? Yeah, so we want to take that pointer that they give us, and where do we want to move that pointer?
Up 4.
Up 4, or down 4. Yeah, decrease it by 4, right? So we increase it by 4 to give it to them, which put it into the structure. But now we want to move it back up 4, so we're pointing to the start of the structure. So yeah, that's exactly what it does. So to take that memory they give us and turn it into a chunk, they take that pointer, cast it to a pair star again, and subtract size of t. And now, bam, we're back to that memory that we called sbrk on. And now we can get the size to free, right? Now we know exactly how many bytes they asked for when they allocated it. We gave it back to them. And now we can do other stuff. We can call sbrk. So what is the big problem with this way we've done it here, where we call sbrk every time they give us memory, and then we just call minus sbrk every time we want a free memory?
It takes a lot of time.
What was that?
It takes time.
It takes time? Yeah. What else?
They could free something. They could allocate units and free the first.
Right, exactly. The way we were doing it, right? You alloc, malloc, malloc, malloc. What if I wanted to free the thing, the very first thing that I malloced, right? If I'm just moving the sbrk pointer, the heap, I'm going to accidentally free all that stuff or not free that stuff, right? It's going to be a problem. So you can think as the heap only grows up or down, right? But it's not, the heap can't just free one thing that's on the bottom, yeah.
How does it know that where those in-between spots have been free?
Exactly, is the question. Yeah, so that's the thing, right? So what we looked at was kind of super simple malloc, but even that's too simple to actually function, because we need to be able to free something that's not exactly below us. And let's say you allocate a bunch of things, right? They're on the heap in this order, and then you free from bottom up, free. Well, now maybe what we're talking about, maybe I want to call sbrk and free all that memory, but how do I know that all that memory was actually deallocated by the programmer? So this is kind of a very high level of how it actually works. So the basic idea is, so it's going to call, malloc's going to call sbrk to move the heap up some size, and that's going to change the heap. And the program, malloc gets a pointer to the start of that new memory. And then what it does, it actually not only thinks about chunks in terms of memory that it gives to the programmer, it thinks about chunks also in free space. So it says, I have this whole space that's free. So I can say, hey, I've got a free chunk. I know how many bytes it is because I know exactly how many I asked for from this offset. So I know this is the many bytes I get. Great. So I know this is all free. And it keeps the pointer to basically, let's say, the first free chunk. Then when the program asks for a chunk, it splits the free chunk into 2 chunks and says, okay, how many bytes did you want? Great, 4 bytes. Okay, I need 4 bytes plus, let's see, if I do this in my head, 24 bytes for overhead. So I'm going to actually allocate 16 bytes. Wait, that's not right. Yeah, 16 bytes, so 12 bytes overhead. So 4 and 16, so I'm going to allocate this. But I've kept a pointer to this, and so when I may want to go to the next one, so it actually uses a doubly linked list. So each of these chunks of memory has pointers to the next chunk of memory and has pointers back to the last chunk of memory. And each chunk has a little flag that says if it's free or not. So when it needs to allocate more memory, it goes to the first element of this list. It's actually more complicated, but conceptually it goes to the first element and says, okay, are you free? No, you're not free. Okay, great. Go to the next one. Hey, this one's free. And then it asks, is there enough memory here? Yeah, it's a tiny request. So bam, split this up, allocate some more memory here, make new pointers, make the pointers all nice. And now when we want to free the first memory, we know exactly how to do that, right? Because when the programmer says, I want to free this chunk of memory. And we go, okay, great. I can tell from this chunk of memory the size that you've allocated, and I have pointers to the next memory and the previous memory. So I can make myself free, and in this case, that would just do that. And then if they want to allocate a small chunk of memory in here, well, I could say, okay, is this smaller than this chunk I already have? and now I made more pointers in here. So this is all it is all this list where it's just keeping track of what memory is free, how it can free things. And it goes on, if it needs to do more, it'll do more, all that kind of stuff. So anyways, lots of cool stuff. Yeah, it's really interesting. Modern malloc is very complicated. They keep different buckets for different sizes of memory, so that may be why when we asked for a lot of memory, it actually allocated a bunch and then gave us back from that. But anyways, great. I will see everybody in a week.